Yes, good morning all. Am I audible? Yes, am I audible to you all? Yeah. So I want you all to write down this problem. So this problem now what we got to solve is on Stater-Phillips formula. Okay. Stater-Phillips formula problems we have to solve. So I want you all to write down this problem. Problem 1. A stream saturated with DO has a flow. A stream saturated with DO has a flow. So in the question starting itself, the starting statement, read it carefully. The stream saturated with DO. That means the stream is saturated with a DO. That means streams DO is saturated. The dissolved oxygen of the stream, it's saturated. That means we had learned in the oxygen sag curve, that is there are certain DOs, saturation DOs at certain temperatures, right? At 0 degrees Celsius, it is 14.63 mg per liter, right? At 30 degrees Celsius, as the temperature increases, the DO decreases. At 30 degrees Celsius, it becomes 7.62 mg per liter. And at 20 degree in between, it is 20 degrees Celsius, it will be 9.17 or 9.2 mg per liter. So the DO decreases as the temperature increases. When it was 0 degrees Celsius, the temperature will, when it's 0 degrees Celsius, the DO will be 14 mg per liter, 14.62 mg per liter. That is the highest DO. That's the maximum DO of a stream water. That is stream, saturated stream. Okay. So here the stream is saturated with the DO. That means the DO of the stream will be saturated with a flow of 1.2 mg per liter. Sorry, meter cube per second, with a flow of 1.2 meter cube per second. That is, flow means discharge. With the discharge of the stream has 1.2 meter cube per second. BOD is 4 mg per liter. So BOD is less. Okay. BOD is 4 mg per liter. If it receives the effluent discharge of 0.25 meter cube. So effluent, that is the wastewater discharge, is 0.25 meter cube per second, having a BOD of 20 mg per liter. So the effluent has a BOD of 20 mg per liter and DO of 5 mg per liter. So DO of the wastewater, that is effluent, wastewater or the effluent, is 5 mg per liter. The average velocity of flow of stream. So this is the flow of stream. Velocity of flow of stream is given as 0.18 meter per second. 0.18 meter per second. Then calculate the DO deficit at a point of 20 and 40 kilometers. So we have to find out DO at point of 20 kilometer and 40 kilometer in downstream. Okay. Assume that temperature is 20 degrees Celsius throughout. So temperature of the water stream is 20 degrees Celsius throughout. So when it is 20 degrees Celsius throughout, the BOD will be measured at 5 days and saturation DO is taken as 9.17 mg per liter. Sometimes what happens is they might not give you the saturation DO, but they might give you the temperature of the stream, that is 20 degrees Celsius or 30 degrees Celsius or 0 degrees Celsius. So based on the temperature what is given to you, you have to assume the DO. So basically, if they give you 30 degrees Celsius, you have to assume it as 7.62. If they give you 20 degrees Celsius, it is 9.17. If they give you 0 degree, that is most probably they will not give you 0 degree. So if they give you 0 degree Celsius, it is 14.6362 mg per liter. Then K value and R value is given. K is nothing but deoxygenation constant or deoxidation coefficient of deoxygenation, and R is reoxygenation constant or coefficient of reoxygenation. Okay. I hope you have written this problem. Have you all written the problem? Please write down the problem. You can reply in the chat if you have written down the problem. Yes, is it done? Is it done, students? Problem? Have you written down the problem statement? Please reply. Till R is equal to 0.3. Till that much you have to write down. That is the problem statement. Yes. Have you written? So problem, I'll just tell it once again. A stream saturated with a DO has a flow of 1.2 meter cube per second, BOD of 4 mg per liter. It receives an effluent discharge of 0.25 meter cube per second, having a BOD of 20 mg per liter and DO of 5 mg per liter. The average velocity of flow of stream is equal to 0.18 meter per second. Calculate the DO deficit at 0.20 kilometers and 40 kilometers in the downstream. Assume that temperature is 20 degrees Celsius throughout BOD. Throughout the BOD is measured at 5 days. Take saturation DO at 20 degrees Celsius is equal to 9.17 mg per liter, and K value, that is nothing but deoxygenation coefficient or deoxygenation constant, that is 0.13, or coefficient of reoxygenation, and coefficient of reoxygenation is 0.3, or reoxygenation constant as 0.3. Have you written this much? Please reply. Okay. Okay, so please tell your friends to study this problem. This very important problem from second module. So today many are absent, I think so. Many have not joined. It's very important problem. Okay, so you have to write down. First, we'll write down the Stater-Phillips formula. So whenever you explain the oxygen sag curve, right? You know the oxygen sag curve, right? That is, it'll be showing a graph. Here is the time of flow, and here is the percentage of saturation. Percentage of saturation of what? Dissolved oxygen. So dissolved oxygen percentage of saturation will be showing. And initial stage that there will be some DO. Later on, DO gets decreased. Yeah. And afterwards, it increases. Right? Right? It happens like this. So there is two things that is taking place there. One is deoxygenation, and another one is a reoxygenation at the same time. Just a second, I'll draw it a little bit neatly. So one will be the deoxygenation, right? Another will be the reoxygenation. Two things are taking place. That is reoxygenation R and deoxygenation. Let us take K. The coefficient of deoxygenation is K. Okay. So some people represent it as KD and KR, or KR, KD and KR. That is a deoxygenation coefficient and reoxygenation coefficient. Then there is an oxygen sag curve that is like this. It's going like this, somewhat like this. It comes and goes up. Right? There is saturation DO. That is 100% saturation. 100% DO when it is there, that is saturation DO. So saturation DO varies with temperature. Okay, you're understanding what I'm telling. DO means dissolved oxygen. That is amount of oxygen which is present inside the water at 100% saturation level. That is when the temperature is 20 degrees Celsius, the DO will be, saturation DO will be 9.17 or 2. 9.17 or 9.2. It will be something that much only. Mg per liter. Mg per liter. Okay. When it is 0 degrees Celsius, it will be 14.62 or something, 62 mg per liter. So this is the maximum dissolved oxygen that can be obtained in a water, because water temperature is always 0 degree. It is the least we can go. So maximum DO that can be obtained is 14.62 mg per liter. Then if it is 30 degrees Celsius, then it is equal to, the DO should what? Increase or decrease? Now tell me. When it's 0 degrees Celsius, the DO will be 14. When it's 20 degrees Celsius, the DO will be 9.7. So what will be the DO at 30 degrees Celsius? Whether it will increase or decrease? Yeah, you can use the chat and tell me. Yes. DO decreases, right? Dissolved oxygen from 0 to 20 degrees Celsius, it started decreasing. So it decreases to 7 point, just it becomes half of that, almost half of that. That is 7.63 mg per liter, mg per liter. So it decreases. So that is how the saturation DO varies. Now, what happens is, you can see here, this is the oxygen sag curve. This is the mainly oxygen sag curve, which is representing both oxygenation and deoxygenation. So at certain point, this point, it will reach the critical DO. That is critical DO, dissolved oxygen, critical dissolved oxygen we can find out. So DO is represented as this much is the DO. This much will be the dissolved oxygen. How much ever will be the dissolved oxygen. So above part is the deficit. Oxygen deficit, we can take it as D. DC. So you should be knowing the difference between oxygen deficit and dissolved oxygen. So dissolved oxygen and oxygen deficit are not the same. are not the same. So what is dissolved oxygen? What is oxygen deficit? So oxygen deficit, we can say it is a difference between two dissolved oxygens. It is a difference. It's just showing a difference between two dissolved oxygens. That is saturation dissolved oxygen, and whatever, at whatever point, what might be the DO that you're finding out. That is, at this point, what is the DO? So bottom part is the DO part. So for critical deficit, that is critical DC, to find out critical DC, it is nothing but saturation DO, saturation of dissolved oxygen, saturation dissolved oxygen minus critical dissolved oxygen. Critical dissolved oxygen, right? This is a critical DO from this part to this part. That will give you oxygen deficit. Oxygen deficit is always represented as D. Okay, so DC. You can say this is a critical. For the critical one, DC. Are you understanding this concept? So never get confused between oxygen deficit, and dissolved oxygen. So dissolved oxygen is always represented as DO, and oxygen deficit is represented as D. And oxygen deficit is difference between the saturation DO and the actual DO. It's always that. It is saturation DO minus actual DO. Actual DO or mixed DO, we can say. Mixed DO or actual DO, whatever is the DO at that point. At this point, what is the DO? DO is this much, the bottom part. Are you clear with this? Please let me know if you're clear. Through the chat, let me know if you understood this concept. If you don't understand this concept, it will be difficult for you to solve the problem. Yes, are you clear with this concept? Any doubt, anything you didn't understand in this concept? Please tell me if you didn't understand some of the points. If you didn't understand, which you didn't understand, I'll explain it once again. So you have to be clear with this topic while solving the problem, because if you want to solve the problem, you have to understand what is this thing. Okay, in simple words, there's a graph. This is a DO sag curve. Okay, this is a saturation dissolved oxygen. So amount of dissolved oxygen which is present in water is this much. That is DO, saturation DO. That is the maximum DO, dissolved oxygen, that can be present. Is a saturation DO. And at certain points, as the water flows, as the effluent is thrown into the water, that is waste material or wastewater is thrown into the river streams, what happens? DO starts decreasing, and after certain moment, it starts increasing. Because of self-purification takes place, right? Self-purification takes place, because of which DO again starts increasing. So at certain moments, where and all, what will be the DO here? This is the dissolved oxygen at different points. And at here, this point, it will be like, it will be critical DO, the least dissolved oxygen. That is the minimum will be the critical dissolved oxygen. And then again, it starts increasing. Now, the top part, that is this part, you can see, the top part of that curve will give you the difference between the saturation DO, this is saturation DO, and the dissolved oxygen, actual dissolved oxygen. So difference between the saturation DO and the actual dissolved oxygen is the oxygen deficit. It is D, oxygen deficit D. If you're clear with this concept, we can continue with the problem. Are you clear with this concept? Yes. Okay, so if there is no doubt, I'll continue anyway. So now what is there in the question, we can write down first. The first thing which is given is a stream is having a saturated DO. Okay, That means it is having a maximum DO at a saturation point. At some certain temperature, some saturation DO is there. Now, has a flow of 1.2 meter cube per second. That means discharge of the stream. We can take S as the QS as discharge of stream. QS is equal to 1.2 meter cube per second. Next one, BOD of stream is 4 mg per liter. So BOD we can take it as L. L we can represent, BOD can be represented as L, or else we can represent it as Y. Okay. So L of S we can take, or Y of S. That is BOD of stream is equal to how much? 4 mg per liter. So always BOD, dissolved oxygen, dissolved oxygen, BOD will be in units of mg per liter. The units for BOD and dissolved oxygen will be mg per liter. So never get confused for that. Okay. Next one. If it receives an effluent discharge of 0.25 mg per liter. So effluent means wastewater discharge. Let us consider QE as wastewater discharge is equal to QE as wastewater discharge is equal to 0.25 meter cube per second. So that is given in the question. Next, having a BOD. So let us take the BOD L of E. L of E, okay, is equal to how much? 20 mg per liter. So BOD will be always more for wastewater. For wastewater, the BOD will be very large. For the stream, it is less. Right? For the stream or the water or river water, it will be less. Next one. What is given? DO is given for effluent, right? And the DO we can take it as DO itself, DO, dissolved oxygen of effluent is given as how much? 5 mg per liter. So I want all of you to write down these statements, whatever I'm writing. This is from the question. What is there given in the question? So same thing, I'm writing it down. Next, the average velocity of the stream. Okay, so velocity of the stream is given. We can take velocity of stream Vs is equal to how much? 0.18 meter per second. So velocity will be in meter per second. Next, calculate the dissolved oxygen at a point 20 kilometers and 40 kilometers. So we have to find out dissolved oxygen DO at 20 kilometers. Remember, there is difference. Always there is a difference between dissolved oxygen and oxygen deficit. Don't forget the difference between dissolved oxygen and oxygen deficit. That's why I explained in the first step. I explained what is oxygen, dissolved oxygen and oxygen deficit. So there was a question. BOD of wastewater is 20 or 25. So BOD of wastewater is 20. Sorry, yeah, it's 20. It's not 25. It's there in the question 20. Yeah, sorry, made a mistake there. So BOD of wastewater, that is LE, wastewater or effluent. So E means effluent. Don't get confused. You can write it L of W also. It's wastewater. So what happens is many people make a mistake there because some will confuse wastewater with normal water, as when you write LW, normal stream water or something. So to better understand, S means stream. You can write it here. S means stream. And E means effluent. Okay. S means stream and E means effluent. You can write it down to the side. Okay, we have to find out dissolved oxygen. So never get confused between deficit and dissolved oxygen. We have to find out the dissolved oxygen at 20 kilometers and dissolved oxygen at 40 kilometers. You know what does this mean? what happens is, so you just take an example here. You can see here, this is a reeve. It's a downward stream. It is going in a downward slope, downslope stream. So initially, we can state it as 0 kilometers. That is, we have not started the stream. So at this stage, that is 0 kilometer stage, that is this stage, we are dumping the water. Normally, the stream will be not 0 kilometer. It will start from the mountain areas and all. So in between, this is stream. Like this stream is going, and here you are having a wastewater pipeline. Your effluent pipeline, we can say effluent pipeline. So wastewater pipeline. So effluents are discharged at the 0 kilometer stream. Okay, so effluent is discharged here. Now what happens? As the downslope goes down, the water dissolved oxygen at the initial stage will be very less, because the dissolved oxygen in the effluent also will be less. But as the time passes by, it gets purified a little bit. But the reason why it gets diluted, right? The effluents get diluted in the stream, because of which, since the stream is larger in quantity than the effluent, it gets diluted in the stream, and the dissolved oxygen again starts increasing after certain point. So at 20 kilometer, what is the dissolved oxygen? And at 40 kilometers, what is the dissolved oxygen? We have to find out. So from 0 to 40 kilometers and 0 to 20 kilometers, what is the dissolved oxygen that we have to find out? Are you clear? Are you clear with this? Okay, so these two things we have to find out. Then what is given to us? Let us see. Assume that the temperature is 20 degrees Celsius throughout. BOD is measured throughout, and BOD is measured at 5 days. Okay, so temperature throughout. So all throughout, the temperature will be 20 degrees Celsius. So sometimes what happens is, they might change the temperature based on the requirement. That is, based on the like sometimes the stream will be having different temperature and effluent will be having different temperature. So we have dealt with the same kind of problem in the previous problem. We have done, right? In the previous problem, there was temperature, certain temperature for the stream, different temperature, and different temperature for the effluent. So we had to find out the mixed temperature, right? Do you remember that? Please let me know if you have done the previous problem. In previous problem, we have found out BOD mix, DO mix, and temperature mix, right? So what does BO mix, BOD mix and DO mix and temperature mix means? It means the combined combination of the temperature, BOD, and dissolved oxygen of effluent as well as the stream we are finding out. Okay. So in previous question, they had given you two different temperatures, right? One was 25 degrees Celsius and another was 16 degrees Celsius. Do you remember that? Please let me know. I don't know whether you're understanding this or not, because it will be difficult for me to explain until you understand this concept. In the previous, we had found out temperature mix, right? Temperature mix. The temperature was two different temperatures. One was for the stream, another one was for the effluent. And you know the formula, that is QSCS plus Q effluent plus Q effluent into C effluent divided by QS plus QE. So this is the formula that we use for finding out any concentration. The concentration, that is C, we have to, if we want to find out the C, we use this formula. Or C mix, we can say C mix if you want to find out, or combined combination if you want to find out, we are using this formula. And this formula can be used to find out the BOD, that is the L, BOD, or DO, or temperature. So this we used in the previous problem to find out the BOD, DO, and the temperature of previous problem, right? Do you all remember this? See, I wasted half an hour like to explain you this itself. If you're clear, please let me know. Yes, I'm clear. Else it will be difficult for me to understand whether you're understanding it or not. Okay. So that is formula used for finding out BOD, dissolved oxygen, as well as the temperature. Now here what they have given is a common temperature. So temperature is given as 20 degrees Celsius is common for all, both the effluent as well as stream. Next thing what it's given is okay, just a second. Yeah, next thing what it's given is take saturation DO as at 20 degrees Celsius as 9.17. Saturation DO is only for the stream water. Always saturation DO will be there for stream water. So therefore, dissolved oxygen for what? Stream is given as 9.17 mg per liter. So it is dissolved oxygen for stream. It will come here somewhere. We can write it. Dissolved oxygen for the stream is given as 9.17 mg per liter, that is at 20 degrees Celsius. Okay. Then we have given with the values K, or we can take it as KD. So whatever you want, you can take it, KD or K. That is dissolved deoxygenation coefficient. Deoxygenation coefficient, we can take it as 0.13, and reoxygenation coefficient, that is R or KR, you can take it as 0.3, which is these things are given in the question. Okay, these things are given in the question. Now, Stater-Phillips equation is the first thing that you need to know first. That is, Stater-Phillips equation states that according to Stater-Phillips equation, oxygen deficit at any time t, oxygen deficit, that is D, at any time t is equal to K L naught, K means KD itself, K L naught divided by R minus K, that is reoxygen coefficient minus K, K, R minus K in whole bracket multiplied by 10 to the power minus K T. So same T at what time, what we are taking. See, T is the time. Okay, not the temperature. So always remember, T is not the temperature, it is representing time. Where whenever we talk about temperature, we are representing in TEMP. Temperature is equal to TEMP. We are representing as TEMP. For time, we are taking it as T. So don't get confused with that. T is equal to time. Okay. Minus 10 to the power minus RT, that is time, plus D naught. It's not DO, it's D naught. It's not DO, it's D naught. That is oxygen deficit at initial stage. So when the this curve starts, right? So at initial stage, the D naught value. Initial stage, what is the D naught value? That is the difference between saturation DO and the. So it's the difference between the saturation DO and the actual DO at initial stage. That is D naught into 10 to the power minus RT. So write down this formula. I want all of you to write down this formula. So this is the Stater-Phillips equation. Stater-Phillips equation. This is the Stater-Phillips equation. So I want all of you to write down the Stater-Phillips equation. Okay. Then to find out D naught, that is initial oxygen deficit, we are finding out the oxygen deficit at initial stage will be D naught is equal to saturation DO, it is saturation DO minus DO mix or actual DO. Actual DO or DO mix. So both are same. Actual DO or DO mix, both are same. Okay, so you can write down this formula also. Initial oxygen deficit, initial oxygen deficit, initial oxygen deficit. D naught is nothing but initial deficit. Okay, so D naught is initial oxygen deficit. So for finding out the initial oxygen deficit, we have this formula, that is D naught is equal to saturation DO minus actual DO or DO mix. Both are same. Actual DO or DO mix, both are same. Okay. And L naught, this one, L naught. So these and this one, these are the two things that we need to find out initially. L naught is initial BOD, which is equal to LT or L5, we can say, minus, so divided by L5 divided by, actually the formula is different for this, but you can use this formula also. That is 1 minus L5 minus 1 minus 10 to the power minus KT. Okay, so this is the formula to find out L naught. Actually, the formula is L5. So L5 is nothing but BOD, right? It's BOD. L means BOD. BOD at fifth day. BOD at fifth day, that is nothing but BOD of mix. Similarly, how we had actual DO and DO of mix, same way BOD of fifth day and BOD of mix are same. Okay. So BOD of mix is equal to L naught into 1 minus 10 to the power minus KT. So this was the formula, actual formula. So to find out L naught, we are just dividing L5 or L mix, that is BOD mix, divided by 1 minus 10 to the power minus KT. So these three formulas you have to remember if you want to solve the problem. So make note of these three formulas. DT is oxygen deficit at time T. Okay, at time T. D naught is I think the time is running out now, so we'll end the meeting here itself, class here itself. Next class, I'll continue the session. Yes, can you all hear me? Yes. Hello, Pavitra? Pavitra, can you hear me? Just take the attendance fast. I think time is running out. I'll continue with the problem next class. Pavitra, are you there? Okay, just take the attendance fast.